In the last few videos, we learned how to sketch polar curves and how to find the area enclosed by them. We built the intuition that finding area in polar coordinates is like taking smaller and smaller sectors under the curve. From that idea, we derived the general formula for polar area. In this video, we will go much deeper into polar area and integration through several more advanced examples. First, we will learn how to find the intersection points between different polar curves. This is essential because in many area problems, we need to know exactly where the curves meet. After that, we will reinforce another powerful technique that we touched on in the previous video, symmetry. Through multiple examples, we will see how symmetry can make polar area problems way easier. Next, some familiar curves will return to the scene, including spirals and exponential curves, and we will learn how to find the area enclosed by them. One scenario we will explore is what happens when the curve is flipped. Another important case is when curves intersect inside the region of interest. Sinusoidal circles will also be covered, and we will learn how to find the enclosed area between them. From there, we will investigate how the area changes when the curves are moved around or rescaled. And of course, finding area enclosed by cardioids will also be covered, and we will cover multiple further examples beyond what we have seen here. If you do not yet know what polar coordinates are, how to sketch polar curves, or how the polar area formula works, I recommend watching the earlier 3 videos in this series first. They are linked in the top right corner of the screen and are also in the video description below. Firstly, we need to learn how to find intersections of polar equations. For our first example, let's consider a cosine function. We already know that this curve is a circle with radius 1. The other function is cosine of 2 theta. From earlier, we know that this produces a rose curve. To sketch it, we typically need 2 sample points, especially those that don't lie on the axis. The 2 curves intersect at 4 different points, as shown by the black crosses. To find the coordinates of these intersections, we equate the 2 polar functions. We then apply a trigonometric double angle identity to the right-hand side. Next, we rearrange the equation into quadratic form. This quadratic can then be factorized, which gives us 2 possible cases. Taking the inverse cosine of both sides gives us 4 unique values of theta. These correspond to the angles of some of the intersection points. We can then substitute each theta value into either polar function to obtain the corresponding r values. Doing so gives us the green and orange intersection coordinates shown here. Notice, however, that the 2 purple coordinates actually represent the same purple cross. However, we also have an intersection at the origin, as shown here. Why did we not obtain this as a solution? This is because in polar coordinates, intersections at the origin must be checked separately. To do this, we first set the blue curve equal to 0. This gives 2 unique values of theta. We then set the other function equal to 0, and this gives 4 unique values of theta. Since both functions have valid theta values that make the function value equal to 0, that means there must be an intersection at the origin. In polar coordinates, when r equals 0, the point is at the origin regardless of the value of theta. Therefore, it does not matter that the theta values obtained from the blue and red functions do not match. For our next example, let's consider a tangent function and a sine function. We begin by sampling points for the tangent function. Doing so gives us a U-shaped curve and an inverted U-shaped curve. Next, we sample points for the sine function containing a double angle. We already know that this should produce a 4-petal rose curve, but it's still helpful to calculate some points, especially those that are not located on the axis. To determine the intersection points, we set the two functions equal to one another. From our trigonometric identities, we know that tangent theta can be written as sine theta divided by cosine theta. We also apply the double angle identity for sine 2 theta. Rearranging the equation gives us the following form. The next step is to factorize the equation. Either factor can be equal to 0. Solving these equations produces several possible values of theta. Let's arrange these values in ascending order. As we move down the list, the value of theta increases. For each angle, we can calculate the corresponding r value using either polar function. To make the values easier to interpret, let's rewrite the angles in decimal form. And the first coordinate corresponds to the origin. Unlike the previous example, where we had to perform a separate check for the origin, it already appears here as one of our solutions, and so no additional check will be required later. We can now work through the remaining coordinates and plot crosses at the corresponding intersection points. Notice that not all of the coordinates are unique. Several of them have an r value of 0, which means they all represent the origin. At this point, we have identified all of the intersection points. The same approach can be used to find intersections regardless of the polar function involved. For example, suppose we had a simple sine function instead. Or perhaps the coefficient was larger, producing a 3-petal rose curve. In fact, the exact same method works for any polar function. Now that we have learned how to find intersection points, let's move on to our first area example. This time, we will work with an exponential curve and a spiral curve. First things first, we sample a sufficient number of points to sketch both curves. They may look somewhat similar at first because both spiral outward, but the exponential term grows much faster than just theta. From this, we can see that the two curves do not intersect in the current form. Let's say we place one green boundary line at an angle of 1 radian. Then we place another boundary line at an angle of 2 radians. Our goal is to find the area enclosed by these 4 boundaries, which is shaded in orange. But how do we actually calculate it? Notice the pink region below the orange region. That represents the area under the red spiral function from 1 radian to 2 radians. When we combine the orange and pink regions, we get the total area under the blue exponential function over the same interval. So we can first calculate the area under the blue curve, and then calculate the area under the red curve, and finally subtract the two. The difference gives us the orange region. Applying our familiar polar area formula, we set up the difference between the blue and the red expressions. Next, we square both the blue and the red parts. After integrating, we obtain the following result. Substituting the angle limits gives us 10.64. Therefore, the area of the orange region is 10.64 square units. So that was pretty straightforward, or at least I hope it feels that way now. When we decrease the angles of the boundary lines, all we are really doing is changing the limits of integration. The same method still works between any two angles like this. Now let's make the problem a bit more difficult by adding coefficients in front of both functions. Suppose we increase the coefficient of the spiral and decrease the coefficient of the exponential curve. If we blindly use the formula without checking the graph, we can run into trouble. In this case, the result becomes negative, which tells us something is wrong with the order of the expressions. Looking at the graph, we can see that the red function is larger than the blue function, at least between the two green boundary lines. So to calculate the area, we need to reverse the order of the expressions inside the integrand. Now, let's increase the difficulty even further by reducing the spiral's coefficient to 2 and changing the angle limits. And this time, the two curves intersect within the interval that we are considering. As a result, the shaded region is split into two parts, orange and pink. Once again, this shows why we should not blindly apply formulas without first understanding the graph. We first need to find the intersection point by setting the two functions equal to each other. From there, we can simplify the equation like this. This equation cannot really be solved analytically, but using Newton's method, we can approximate the solutions shown here. In the future, I will make a video on Newton's method, and the link should appear in the top right corner of the screen, or in the video description below. For now, just trust that these are the solutions. Although there are two intersection points, only one of them lies between the two green boundary lines. So the point we care about is the one with the larger angle value. At this angle, the R value is approximately 4.31. The angle itself is approximately 2.15 radians. To find the area of the orange region, we subtract the blue expression from the red expression, because the red curve is farther from the origin over this interval. Evaluating the integral gives us 1.81. For the pink region, the order reverses. This time we subtract the red expression from the blue expression, because the blue curve is farther from the origin over that interval. Evaluating the second integral gives us 2.74. The total area is simply the sum of these two parts. Adding them together gives us approximately 4.55. Now, let's change the equations into sinusoidal polar functions. In this case, sampling points is not really necessary, because we can sketch them directly as circles that pass through the origin. Our goal is to find the area of the purple region. Let's first draw a vector pointing to the red curve. As the angle increases to 0.25 pi, we reach the intersection point. We know this happens at 0.25 pi because these are the standard sine and cosine functions. The area swept out by the red curve from 0 to 0.25 pi is shown in orange. Next, we continue sweeping the angle all the way to 0.5 pi, or 90 degrees. The area covered between 0.25 and 0.5 pi is shaded in green. Now, let's bring back the purple region that we were originally interested in. When we switch back, we can see that the green region forms half of the purple region, while the orange region is not actually useful for our final area. Next, let's create a vector pointing to the blue curve at 0.5 pi. As we sweep the vector down to 0.25 pi, it covers the orange region. Then we sweep to 0 radians, which gives us the green region. Now, let's bring back the areas swept out by the red curve. Then we switch back to the areas swept out by the blue curve. From this comparison, we can see that adding the green region from the blue curve to the green region from the red curve gives us the target area, which was originally shown in purple. To make the idea clearer, the red shaded region belongs to the red curve, while the blue shaded region belongs to the blue curve. The red region is the area swept out by the red curve from 0.25 pi to 0.5 pi, as we saw earlier. To calculate this area, we first square the cosine term. Next, we apply the trigonometric identity for cosine squared theta. After integrating, we obtain this expression. Evaluating it at the limits gives us the exact answer here. Let's move the answer onto the grid. Now, the blue area is the area swept out by the sine curve from 0 to 0.25 pi. To calculate it, we square the sine term. Next, we apply the corresponding trigonometric identity. Integrating the expression gives us this form. After substituting the limits, we obtain this answer. We get the same result as the red area. This was expected because the standard sine and cosine curves are symmetric here, so the two swept areas are equal. The total area is the sum of the red and blue areas, so we simply add these two values together. This gives us the total enclosed area. Let's reinforce one important idea. Recall that the blue region is the area swept out by the blue curve from 0 to 0.25 pi. The red region, on the other hand, is swept out by the red curve from 0.25 pi to 0.5 pi. The value of 0.25 pi is important because it marks the intersection point. That intersection determines where we split the limits of integration. In this case, we already knew what this angle was, but if we did not know it, we could find it by setting the two functions equal to each other. From there, we could rearrange the equation like this, and this allows us to rewrite the expression using the tangent. So we get tangent of theta is 1, which gives theta of 0.25 pi within this interval. If we had not known the intersection angle beforehand, this type of calculation would have given it to us. If the sine and cosine functions contain additional parameters, we may have to calculate the intersection points manually. Changing those parameters alters the positions and shapes of the curves, so we may no longer be able to tell the intersection angle by intuition alone. And if one of the curves has a completely different shape, then relying on intuition becomes even less reliable. Now, let's add a few more parameters. We also zoom out slightly so that the full curves remain visible. Next, we transform both curves into cardioids. From there, we can simplify the equations. We'll continue this cardioid example along with several other examples in the next video. Before you move on, please consider liking, commenting, and subscribing to support the channel. The next video should be on your screen right now. Click it to continue, or you can find it in the video description below.